Hello, welcome to Project 4, Constructing an ADC for Use in Sensing Systems. We can use our ADC for applications beyond measure, but a few are seen here. We can use it for a neural sensor to detect brainwaves, reading temperatures from a room, reading ambient light waves, low signal from an ambient light sensor on a phone. We could even use it for reading tiny sounds in a very sensitive noise sensing environment. The applications are many, but the system is fairly simple. You take your low-level input voltage of about 100 millivolts, pass it through an amplifier with about a gain of 40 decibels. The bandpass filter is generally low-pass due to the nature of our input signals. This is for the neural applications specifically. It could be for others, it didn't necessarily have to be a low pass, and then run it through the ADC to get your output. We focused on the ADC design in this project. Here we see the overall schematic of the ADC. It has three main components: the square wave generator, the sample and hold circuit, and the comparator. These three components work together to become the ADC that you will see the output of later. Note the ramp generator also used to be an input to the sample and hold circuit. Here we see the detail circuit of the square wave generator. The input current is created by two floating gate switches in series with a total bias current of about 13 nanoamps. These are then used to charge a cap which discharges, which cycles the T-gate switch, which produces the square wave, the output of which can be seen here. Note the non-linearities on the top end, likely due to the leakage in the DAC on the board. Note that this square wave is not an exact representation of the one we used, because the one we used cycled too quickly and above the DAC's sampling rate. Here we see the details of the sample and hold circuit. It consists of the digital input, a T-gate, and the ramp generator that we'll show the output of on the next slide. Here's the ramp generator output. It was sampled at around 200 Hertz and it has a full scale range of 1 volt. This is due to the fact that if the MOSFETs drop below 0.7 volts on the chip, they fall out of saturation and the output gets very messy. Here we see the output of the sample and hold circuit. Note the nonlinearities, specifically the increase in both what is supposed to be the flat region and here, which is steeper than normal. This is due to the capacitance of the routes in the FPAA causing more charge to be pumped into the output, as we discussed in class. In this graph, we see the real output compared with the idealized output. In this graph, we see the linearity of the system. The dotted line in this graph represents a line drawn through the midpoint of each of the idealized steps. The blue dotted line in this graph represents a line drawn through each of the steps in the real output. You can see these are fairly close with an R-squared of 0.9961. This indicates a linear system through the 9 bits. You can see it's 9 bits because we get about 4,000 steps through the system, which means that we were able to encode 4096 values. However, there are clearly not 2 to the 16 steps in either the real output or the matched idealized output. This is because in the real output there are about 2 to the 16 levels, but they could not accurately be represented by the DAC on the system that has a low resolution not high enough to accomplish this. Here, we see calculations for the system. The least significant bit was about 4 millivolts, and the INL and DNL were taken by comparing the the real and idealized graphs on the previous page. The values you see here were obtained by applying these formulas to each step in conjunction with the previous step. Thank you very much for watching. and have a nice day and weekend. That's better.